Relativity, the Special and General Theory by Albert Einstein. Sections 16 and 17. Section 16. Experience and the Special Theory of Relativity. To what extent is the special theory of relativity supported by experience? This question is not easily answered for the reason already mentioned in connection with the fundamental experiment of Fizeau. The special theory of relativity has crystallized out from the Maxwell-Lorentz theory of electromagnetic phenomena. Thus, all facts of experience which support the electromagnetic theory also support the theory of relativity. As being of particular importance, I mention here the fact that the theory of relativity enables us to predict the effects produced on the light reaching us from the fixed stars. These results are obtained in an exceedingly simple manner, and the effects indicated, which are due to the relative motion of the earth with reference to those fixed stars, are found to be in accord with experience. We refer to the yearly movement of the apparent position of the fixed stars, resulting from the motion of the earth round the sun, aberration, and to the influence of the radial components of the relative motions of the fixed stars with respect to the earth, on the color of the light reaching us from them. The latter effect manifests itself in a slight displacement of the spectral lines of the light transmitted to us from a fixed star, as compared with the position of the same spectral lines when they are produced by a terrestrial source of light. Doppler principle. The experimental arguments in favor of the Maxwell-Lorentz theory, which are at the same time arguments in favor of the theory of relativity, are too numerous to be set forth here. In reality, they limit the theoretical possibilities to such an extent that no other theory than that of Maxwell and Lorentz has been able to hold its own when tested by experience. But there are two classes of experimental facts hitherto obtained which can be represented in the Maxwell-Lorentz theory only by the introduction of an auxiliary hypothesis, which in itself, i.e., without making use of the theory of relativity, appears extraneous. It is known that cathode rays and the so-called beta rays emitted by radioactive substances consist of negatively electrified particles, electrons of very small inertia and large velocity. By examining the deflection of these rays under the influence of electric and magnetic fields, we can study the law of motion of these particles very exactly. In the theoretical treatment of these electrons, we are faced with the difficulty that electrodynamic theory of itself is unable to give an account of their nature, for since electrical masses of one sign repel each other, the negative electrical masses constituting the electron would necessarily be scattered under the influence of their mutual repulsions, unless there are forces of another kind operating between them, the nature of which has hitherto remained obscure to us. Footnote. The general theory of relativity renders it likely that electrical masses of an electron are held together by gravitational forces. End footnote. If we now assume that the relative distances between the electrical masses constituting the electron remain unchanged during the motion of the electron, rigid connection in the sense of classical mechanics, we arrive at a law of motion of the electron which does not agree with experience. Guided by purely formal points of view, H.A. Lorentz was the first to introduce the hypothesis that the particles constituting the electron experience a contraction in the direction of motion in consequence of that motion, the amount of this contraction being proportional to the expression the square root of the difference I minus the fraction v squared over c squared. This hypothesis, which is not justifiable by any electrodynamical facts, supplies us with that particular law of motion which has been confirmed with great precision in recent years. The theory of relativity leads to the same law of motion without requiring any special hypothesis whatsoever as to the structure and the behavior of the electron. We arrived at a similar conclusion in section 13 in connection with the experiment of Fizeau, result of which is foretold by the theory of relativity without the necessity of drawing on hypotheses as to the physical nature of the liquid. The second class of facts to which we have alluded has reference to the question whether or not the motion of the earth in space can be made perceptible in terrestrial experiments. We have already remarked in section 5 that all attempts of this nature led to a negative result. Before the theory of relativity was put forward, it was difficult to become reconciled to this negative result, for reasons now to be discussed. The inherited prejudices about time and space did not allow any doubts to arise as to the prime importance of the Galilei transformation for changing over from one body of reference to another. Now, assuming that Maxwell-Lorentz equations hold for a reference body K, we then find that they do not hold for a reference body K' moving uniformly with respect to K. If we assume that the relations of the Galilean transformation exist between the coordinates of K and K', it thus appears that of all Galilean coordinate systems, one, K, corresponding to a particular state of motion, is physically unique. This result was interpreted physically by regarding K as at rest with respect to a hypothetical ether of space. On the other hand, all coordinate systems K' moving relatively to K were to be regarded as in motion with respect to the ether. To this motion of K' against the ether drift relative to K', were assigned the more complicated laws which were supposed to hold relative to K'. Strictly speaking, such an ether drift ought also to be assumed relative to the Earth, and for a long time the efforts of physicists were devoted to attempts to detect the existence of an ether drift at the Earth's surface. In one of the most notable of these attempts, Michelson devised a method which appears as though it must be decisive. Imagine two mirrors so arranged on a rigid body that the reflecting surfaces face each other. A ray of light requires a perfectly definite time t to pass from one mirror to the other and back again, if the whole system be at rest with respect to the ether. It is found by calculation, however, that a slight different time t' is required for this process, if the body, together with the mirrors, be moving relatively to the ether. And yet another point, it is shown by calculation that for a given velocity v with reference to the ether, this time t' is different when the body is moving perpendicularly to the planes of the mirrors from that resulting when the motion is parallel to these planes. Although the estimated difference between these two times is exceedingly small, Michelson and Morley performed an experiment involving interference in which this result should have been clearly detectable. But the experiment gave a negative result, a fact very perplexing to physicists. Lorentz and Fitzgerald rescued this theory from this difficulty by assuming that the motion of the body relative to the ether produces a contraction of the body in the direction of motion, the amount of contraction being just sufficient to compensate for the difference in time mentioned above. Comparison with the discussion in section 12 shows us that from the standpoint also of the theory of relativity, this solution of the difficulty was the right one. But on the basis of the theory of relativity, the method of interpretation is incomparably more satisfactory. According to this theory, there is no such thing as a specially favored, unique coordinate system to occasion the introduction of the ether idea, and hence there can be no ether drift, nor any experiment with which to demonstrate it. Here the contraction of moving bodies follows from the two fundamental principles of the theory without the introduction of particular hypotheses, and as the prime factor involved in this contraction we find, not the motion in itself, to which we cannot attach any meaning, but the motion with respect to the body of reference chosen in the particular case in point. Thus, for a coordinate system moving with the Earth, the mirror system of Michelson and Morley is not shortened, but it is shortened for a coordinate system which is at rest relatively to the Sun. End of section 16. Section 17. Minkowski's four-dimensional space. The non-mathematician is seized by a mysterious shuddering when he hears of four-dimensional things, by a feeling not unlike that awakened by thoughts of the occult. And yet there is no more commonplace statement than that the world in which we live is a four-dimensional space-time continuum. Space is a three-dimensional continuum. By this we mean that it is possible to describe the position of a point at rest by means of three numbers, or coordinates, x, y, z, and that there is an indefinite number of points in the neighborhood of this one, the position of which can be described by coordinates such as x sub 1, y sub 1, z sub 1, which may be as near as we choose the respective values of the coordinates x, y, z of the first point. In virtue of the latter property, we speak of a continuum, and owing to the fact that there are three coordinates, we speak of it as being three-dimensional. Similarly, the world of physical phenomena, which was briefly called world by Minkowski, is naturally four-dimensional in the space-time sense, for it is composed of individual events, each of which is described by four numbers, namely 3 space coordinates x, y, z, and a time coordinate, the time value t. The world is, in this sense, also a continuum, for to every event there are as many neighboring events, realized or at least thinkable, as we care to choose. The coordinates x sub 1, y sub 1, z sub 1, t sub 1, of which differ by an indefinitely small amount from those of the events x, y, z, t originally considered. That we have not been accustomed to regard the world in this sense as a four-dimensional continuum is due to the fact that in physics, before the advent of the theory of relativity, time played a different and more independent role as compared with the space coordinates. It is for this reason that we have been in the habit of treating time as an independent continuum. As a matter of fact, according to classical mechanics, time is absolute, i.e., it is independent of the position and the condition of the motion of the system of coordinates. We see this expressed in the last equation of the Galilean transformation. T prime equals t. The four-dimensional mode of consideration of the world is natural on the theory of relativity, since according to this theory time is robbed of its independence. This is shown by the fourth equation of the Lorentz transformation. T prime equals the fraction in which the numerator is t minus the fraction vx over c squared, and the denominator is the square root of the difference I minus the fraction v squared over c squared. Moreover, according to this equation, the time difference delta t prime of two events with respect to k prime does not in general vanish, even when the time difference of delta t of the same events with reference to k vanishes. Pure space distance of two events with respect to k results in time distance of the same events with respect to k prime. But the discovery of Minkowski, which was of importance in the formal development of the theory of relativity, does not lie here. It is to be found rather in the fact of his recognition that the four-dimensional space-time continuum of the theory of relativity, in its most essential formal properties, shows a pronounced relationship to the three-dimensional continuum of Euclidean geometrical space. Begin footnote. Compare the somewhat more detailed discussion in Appendix 2. End footnote. In order to give due prominence to this relationship, however, we must replace the usual time coordinate t by an imaginary magnitude, square root of negative I, ct proportional to it. Under these conditions, the natural laws satisfying the demands of the special theory of relativity assume mathematical forms in which the time coordinate plays exactly the same role as the three space coordinates. Formally, these four coordinates correspond exactly to the three space coordinates in Euclidean geometry. It must be clear even to the non-mathematician that as a consequence of this purely formal addition to our knowledge, the theory perforce gained clearness in no mean measure. These inadequate remarks can give the reader only a vague notion of the important idea contributed by Minkowski. Without it, the general theory of relativity, of which the fundamental ideas are developed in the following pages, would perhaps have got no farther than its long clothes. Minkowski's work is doubtless difficult of access to anyone inexperienced in mathematics, but since it is not necessary to have a very exact grasp of this work in order to understand the fundamental ideas of either the special or the general theory of relativity, I shall at present leave it here, and shall revert to it only towards the end of Part 2. End of Section 17.